Here are some of the things that my team could have bought with the money we saved by running Spot instances. We could have bought each person on the team their own personal Ferrari. We could have literally sent the team on a private space flight. And my personal favorite, we could have bought tickets for the entire team to the next 260 years of SREcon. My name is Lasse. I have a love-hate relationship with Spot instances. Let's talk about it. I'm part of the telemetry team that works on the observability platform at Maersk. The platform runs the Loki, Grafana, Tempo, and Mimir stack on Kubernetes on Azure. The platform consists of about 8,000 pods across 330 nodes across 5 clusters. And for the first 3 years of the platform's lifetime, the entire platform ran exclusively on Spot instances. A Spot instance is a discounted virtual machine that can be reclaimed with short notice. A Spot instance being reclaimed is what we typically refer to as an eviction. Spot instances allow architectures to trade stability for money, and while much of the chaos introduced with Spot instances can be mitigated, we will see that it is extraordinarily difficult for a complex system to not be affected in some way by the instability of Spot instances. All the major cloud providers offer their own flavor of Spot instances with only minor differences, and the expected savings from running Spot instances can be anywhere between 60 and 90%. So for most decently optimized systems, switching to Spot instances is one of the largest potential cost savings. As a quick note, I'm going to be using the terms Spot instance and Spot node interchangeably. They refer to the same thing. So at this point, we might be thinking, why should we care about any of this? Why would we want to voluntarily introduce chaos in our perfectly pristine environments? And the answer here is simple. It's all about the money. Depending on the size of the infrastructure we're running, there is potentially a lot of money on the line by switching to Spot instances. There are a couple different ways that we can run Spot instances, and what I've done here is I've created a highly scientific graph where we have infrastructure cost on the x-axis and misery of running that infrastructure on the y-axis. And in the top right corner, we have what I imagine many people here are choosing to do with Spot instances, which is to not use them at all. This is the sensible choice because it is the most bearable way to run the infrastructure, but relatively speaking, it's also an extremely expensive way to run the infrastructure. We can also run partially on Spot instance. So here, we pick out select workloads in our cluster, typically the stateless workloads, that we think are equipped to handle the instability from the Spot nodes, and then we run those on Spot and the rest on non-Spot. Here we get a compromise in terms of misery and cost, where we're getting the cost savings from some of the workloads that can tolerate it, but for most workloads, we're still keeping them on regular nodes. And then in the bottom left corner, we have the insane person's choice, which is run the whole system on Spot nodes. This is what we did. I can't recommend it for reasons that we will see in this talk. We saved a bunch of money doing this, but it is also absolutely miserable. And in this talk, I'm going to show why. One of the things we learned very quickly is that our workloads absolutely must terminate gracefully. In our system, this is what the architecture of an eviction looks like. The exact architecture here will vary depending on which cloud you run in. We run in Azure, so in our case it looks like this. If you run in other clouds, the cloud platform might do more of this for you automatically. For example, if you run on AWS with Carpenter, that will do most of what's shown here for you. But in our case, we have this set up. So Azure has a scheduled events process that it runs on each of the nodes. So that's not a pod, it's just a Linux process. This process can be polled. It exposes an API endpoint that can be polled to read inbound events for the node. And one of the events that can be found is the eviction event. So we run a Spot handler daemon set, so that's one pod on each node. The Spot handler will regularly reach out to this scheduled events process. It'll ask, do I have inbound events on this node? If it finds that an eviction event is inbound, then it will first cordon the node to prevent new pods being scheduled on the node. And then it will politely ask each pod on the node to terminate. We run on Linux, so in our case, a polite termination signal is just a sig term. And regardless of what the exact architecture looks like here, there are 2 crucial things we're looking for. Number 1, we need a way to know ahead of time, ideally, when evictions are going to happen. And we need to get this polite termination signal to the pods on the node. That's the first thing. The second thing is that the workloads on the node have to actually be set up to listen for this termination signal and not just ignore it. Azure's documentation states that this eviction event will be sent to VMs a minimum of 30 seconds before they're evicted. This does not match our experience in practice. We have many cases, sometimes several per day, where a node was evicted, sometimes without the eviction event happening at all, and other times where the eviction event would happen and then just a couple of seconds later the node would be evicted. This is problematic for some of our workloads. For example, we have a stateful workload that has a write-ahead log that it writes to, and then when it gets a termination signal, it wants to flush recent data to the write-ahead log and then terminate. And if it's forcefully terminated while doing this, then that can corrupt the data on the disk, and then when the pod starts back up again, it tries to replay the write-ahead log, is unable to do so because the log is corrupted, and the pod just starts crash looping, and we have to take some manual action. We could also have some API pods that handle HTTP requests, and when they're terminated, they want to finish handling in-flight requests before they shut down. And if they're forcefully terminated before being able to handle the in-flight requests, then clients will see timeouts and other sorts of connection badness. So we reached out to Azure support to ask, if the documentation states 30 seconds, why do we not see this in practice? And they got back to us to let us know that spot nodes don't have any SLAs, and they basically don't provide a guarantee of really anything. And as frustrating as this was to hear as a customer, I think in some ways it's a perfectly acceptable stance to say that we are buying a heavily discounted product, and part of that deal is that we have to give up some of that safety and stability of regular nodes. Another curious thing we noticed when dealing with support is that we would sometimes spin up nodes that would be bad for a variety of reasons. Typically, it would have some sort of networking fault. And then we would open a support case to try to figure out, is it a problem on our end? Is it in the infrastructure or the data center end, or what's going on here? And often, despite the fact that we would think that kind of issue isn't related to the fact that it's a spot node, Azure support would get back to us by saying, hey, you guys are running on spot instances. Have you considered not doing that? Despite the fact that we would think it's not related to that. So it had that kind of weird effect that it would often derail our support discussions with Azure. Unpredictable eviction patterns will expose gaps in our system's resilience. Let's look at a couple of examples here. So a relatively straightforward example is that we can't run single replica workloads of any kind. If we do so, and an eviction takes out that replica's node, then the entire workload is now down, and the work that it was doing is now no longer being done. In many cases, especially if it's a stateless workload, it'll spin up quickly, sometimes even in a matter of seconds. But there's no guarantee that this is the case. Maybe it can't find a host node, maybe all our nodes are at capacity, and a new node has to be spun up, and that will take some amount of time, almost certainly more than a couple of seconds. Luckily, the solution here is also relatively straightforward. Instead of running single replica workloads, we just make sure that our workloads have more than one pod, ideally a few more than one. This issue is a good example of something that we're also going to see later, where this is a practice that I would consider to be generally good, not running single replica workloads, because even if we're not running on spot, there are many other reasons why our pods can get terminated. And spot nodes will really punish us for not following these generally good practices. Now the next problem, we now have our 4-replica workload, but there's nothing stopping them from just co-locating on the same node, and then if that node gets evicted, now we're back to square one, our entire workload is down, and it's generally a bad time. Kubernetes has this concept of anti-affinity that we can set up to have the workload either prefer or require to run on nodes that don't already have a sibling replica. And there is an assessment to be made here with how aggressive we want to set up the anti-affinity. The most aggressive way to set it up is to say, these pods of this workload cannot run on nodes that already have a sibling pod. The problem with this is that we have some deployments with 500 pods, and we don't have 500 nodes. So each of those pods can't require to have their own special node. Also, in the bottom example here, we've split up our 4-replica workload across 2 nodes. So then when a single node gets evicted, we're down to 2 pods. And even though the workload isn't fully down, if it takes 4 replicas to handle the normal amount of traffic that comes in, then even if we lose 2, that might still be enough to cause regressions in terms of additional latency or failed requests. So on top of anti-affinity, which we've set up on virtually all of our workloads, we've also over-provisioned some of the more sensitive ones to make them more resilient to evictions. There's another class of eviction issues, which we refer to as timing-based evictions. So many workloads in our system do some work on a cadence. And if that workload is evicted at just the right or just the wrong time, if you will, then some problem will emerge. And I've picked just one example here of many. This is actually an example from a couple of years ago that I think illustrates the problem nicely. Back then, we ran the Grafana agent, and the Grafana agent has a disk that it gradually fills up with data. And then once per hour, it'll vacuum the disk to make room for more data. The problem we found the hard way is that the Grafana agent doesn't persistently store the timestamp of when it last vacuumed the disk, but obviously the data on the disk is stored persistently because it's a persistent volume. So we see that here on the slide, that at 8 o'clock the disk is vacuumed, at 9 o'clock the disk is vacuumed, and then at 9:30 the pod gets evicted, starts back up, doesn't remember when it last vacuumed the disk, and just happily keeps filling it up with data, and eventually the disk reaches capacity, we get an alert, and we have to take some manual remediation steps. This class of eviction issue is problematic because it depends on several factors that can change independently of each other. So just with the example here, we have the rate with which the disk fills, we have the disk size, but also the rate of evictions. And all these three things can change independently of each other, both to make the problem more or less likely to occur, but also make the problem more or less severe. Probably the most difficult eviction pattern in our system is multi-zone evictions. So one of the central workloads in our architecture is the Mimir ingester. We run 3 ingester stateful sets, 1 for each of our physical Azure zones. And when an ingester starts, it will register into the ingester hash ring. And each member of the ring will periodically poll all other members to see if they're still alive. If a ring member is unreachable for an extended period of time, then that member is considered unhealthy. And quorum in the ring can be achieved only if 2 out of the 3 zones are healthy, and a write or read will only succeed if quorum can be reached. Crucially, and this is what we should keep in mind on the following slides, it takes only a single unhealthy ingester for that entire ingester zone to be considered unhealthy. So in the example table here, zones A and B are up because they're all healthy, but zone C is down because C1 had a heartbeat that was too long ago. In a normal single eviction scenario, this is not a problem because we still have 2 out of the 3 zones up and we can still achieve quorum. But if 2 nodes are evicted in 2 different zones at roughly the same time, then we're in trouble because now we're down to 1 out of 3 zones, we can no longer achieve quorum, and we start seeing regressions. The ingester workload has a configuration option that we can toggle to say whether they should stay in the ring or leave the ring when they're terminated. And the default behavior is for them to stay in the ring, which causes this problem. So we thought, okay, let's update the ingesters to leave the ring when they're terminated. And that solved this issue, but we discovered a new one. And that's back-to-back evictions. So now, again, 2 nodes are evicted in 2 different zones. We've now updated the ingesters to leave the ring. So in the top right example here, we're still completely fine because the evicted ingesters are not unhealthy in the ring. They're not in the ring at all. Now the ingesters start back up. They start replaying their write-ahead log. This process takes about 10 minutes. And what we found is that if the same ingesters are now evicted again before being able to fully replay their write-ahead log, then they don't leave the ring, and we return to our quorum issue and see various sorts of regressions. This was really a tricky problem that required several different uncommon events to happen at roughly the same time. So we need multiple nodes in the same zone to be evicted within a span of about 10 minutes, because it takes about 10 minutes to replay the write-ahead log. The evicted nodes must have at least 1 overlapping pod. An overlapping pod here means that an ingester that ran on the first node that was evicted then gets scheduled on the second node that gets evicted. And this back-to-back eviction pattern has to happen in 2 different zones at roughly the same time. This particular sequence of events was quite rare. We would see it maybe a couple of times per month. It was extremely difficult to debug, and it would always cause us downtime. Mimir ingesters are not the only component we run that use hash rings. These hash rings are used widely across our tech stack, and unhealthy rings was the most common source of downtime and instability in our system. We had to actually build and run a custom piece of software to monitor these hash rings in our cluster and act if it found them in a bad state. And that brings me to this principle that I think about a lot when we run spot nodes, and that is that chaos compounds. And the wager we're making by choosing spot nodes is we're essentially saying our platform can probably handle every conceivable combination of odd event. And certainly for us, that was not the case. we would find that when just a single eviction happened and nothing else, that would almost always just be fine. Instead, it would be this interaction between the different chaotic elements in our system that would cause downtime. All of the bomb examples here are things that have actually caused us downtime in our production environment. So we could have a network fault plus a Swift eviction. We could have Swift multi-zone evictions, Swift back-to-back evictions. And unfortunately, an absolute classic, which we suffered multiple times, is we could be updating our Kubernetes node pool at the same time as an eviction elsewhere. So the different flavors of eviction here can not only interact with each other, they can also interact with the chaos that's already present in the system. And the examples I've shown are fairly specific to our system, but all systems of any sort of interesting complexity will have their own set of quirks, and it can be really hard to predict ahead of time what they are before spot nodes expose them. When we run on spot nodes, we will have a very high degree of instance churn. Potentially hundreds of times per day, we will be losing nodes to evictions and spinning up new nodes. And this alone can put our system at risk. One thing we learned to not do is to not pin our dependencies in our system. And let's look at an example of how this can cause problems. So we might have a thing-doer workload here. The workload itself is configured to run the latest tag of the thing-doer image. This particular pod is running v2 because v2 was the latest image when it started. Now the pod is evicted, it finds a new host node, it starts back up, and v3 of thing-doer was released, so the pod pulls v3, and despite the fact that we haven't done any manual intervention, this pod is now running a different image ID. And as fate will have it, we find that v3 has some breaking changes and our pod is now crashing. This is also a good example of how spot nodes will punish us for not following a practice that is generally good. Even if we don't run on spot nodes, we probably still want to be pinning our dependencies, also for reasons of security, not just reliability. So there's a whole class of errors that we have come to call on-restart errors. And these are latent issues that are in the cluster that will surface only when a replica is restarted. So at Maersk, we have an internal container registry from where we pull Docker images. And one day, the team that manages this registry pushed a regression that caused all image pool attempts to just fail. So we can see that when this regression is introduced and evictions keep happening in our cluster, eventually we move from a state where we're perfectly fine to crossing that threshold where our cluster can no longer tolerate more down pods. And this entire issue only lasted about an hour end to end. We were able to reach out to the team that manages the registry and they got the change reverted very quickly. Many teams at Maersk that don't run spot nodes, they didn't even realize that this regression had been introduced because they provision new nodes relatively rarely compared to us and thus pull images relatively rarely. But we felt this almost immediately and were the first to let the team know. Another way this manifested was that we run Kyverno in our cluster, and a change was made to Kyverno that caused the provisioning time for nodes to go from less than a minute to about 10 minutes. And because we see more than one eviction every 10 minutes, again, we can no longer, the demand for nodes in our system can no longer keep up with how fast we can provision them. So the same kind of situation here, this time instead of the pods crashing, they're now just in a pending state because they can't find host nodes, but the same kind of pattern emerges that eventually we cross that threshold and we start seeing alerts. We were able to let the Kyverno team know also in this case, and they were able to fix this very quickly. But again, we were one of the only teams that actually noticed this regression. Whenever we spin up a new node, there is hopefully a very low chance, but there is some chance that the node is bad in some way. And I've illustrated that here with the bomb emoji. I consider these to be bomb nodes. And if we're not running on spot nodes and we get a bomb node, then we can drain the node and our cluster is back to a good state. But when we run on spot nodes, there is really no such thing as a good state, or really any such thing as the cluster being in the same state for more than a couple of minutes at a time. So if we get a bomb node, sure, we can drain it, but this process is just going to repeat potentially hundreds of times per day. So even if the chance of getting a bomb node is 1%, that's still at least a couple every single day. We had real trouble finding a good solution to this image. We had lots of discussions internally, and the most promising solution we could come up with was to look at the telemetry from these nodes and to try to find some reliable signals for when a node is a bomb node. The most reliable signal we found is the rate of TCP timeouts on the node. That would indicate some sort of network fault with the node. But even this signal is not perfectly reliable because whether that's a problem in practice depends highly on the pod composition on the node. Also, given the fact that we already have a bunch of chaos just from the fact that we're running spot nodes, our appetite for introducing a piece of software that can identify bomb nodes and then automatically drain them might not be that large because that's just introducing another dimension of chaos, and that software could be bugged and could be draining the wrong nodes and all sorts of badness. So this was really one of the problems that we never actually found a good solution to throughout the whole time we ran on spot nodes, and it cost a lot of toil work. When we initially started running spot instances, we did not have the necessary telemetry to answer questions like, what is the eviction rate across our different instance pools? Was an instance evicted at this specific time where we experienced another issue? And which pods were terminated when this instance was evicted? So what we did was, we built a node evictions dashboard in Grafana, and I'll walk through a couple of things that we can see on this dashboard. The first panel we added here is the panel where we can just see a table of, for a given cluster, which evictions occurred for which node names and when did they occur. This panel helps us to answer the question that all of our reliability investigations start with, which is, did a node eviction occur at the time of this issue or when this alert triggered? So when we have found an eviction that we're interested in, now we can drill down into the logs of the spot handler that we're running on that node. And here we're probing for two things. We want to know, did the spot handler pick up an eviction event before the eviction actually occurred? And then we want to know which pods were running on this node and were they able to shut down gracefully before the eviction actually happened. So this panel allows us to probe for the swift eviction issue that we talked about earlier. One of my favorite panels is this eviction statistics panel. And here we see a count of evictions for each node pool across a 30-day period in this case. And it's important to notice here that these numbers are not adjusted for how many nodes we have of that type. So we're not surprised to find our 96 core nodes at the bottom. That's not because each of those is less likely to be evicted necessarily. That's just because we have very few of those nodes compared to our 8 and 16 cores. But when we do compare the data, the numbers, within the same node pool brackets, then we see a very interesting pattern emerge, and that is that our logical zone 1 consistently gets far fewer evictions across a 30-day period than the other two zones. So this can help us make an informed decision if we have a multi-zone workload that we want to move partially away from spot. So let's say we want to pick 2 out of 3 zones to move away from spot. With this data, we can very confidently say that zone 1 is probably the one that we want to keep on spot nodes because the other 2 zones get far more evictions in the same time range. So I thought this is quite a cool panel. I like this. A metric that we never really found a good way to track is the time that it takes to provision a node. When running spot instances, it's crucial that we can tell both whether we can provision new nodes at all, but also how long provisioning takes. If nodes are being evicted at a rate greater than they can be provisioned, then the system will eventually enter into an incident state. This is what we saw with the Caverno example earlier. A concern which was never realized was being completely unable to spin up new nodes. We always feared a scenario where Azure's capacity was constrained to the point that it was not possible at all to spin up new spot nodes. We did set up a couple of safeguards for this scenario, namely having standby node pools of every SKU, but thankfully we never actually had to use them. Now our system no longer runs exclusively on spot instances. We do still have some workloads that can tolerate it, but most workloads have moved away from spot instances. And I'll show you why. So starting in late May of 2025, we started seeing what we came to refer to as eviction storms in our clusters. These storms evicted a large percentage of a cluster's nodes in a short amount of time, and their intensity varied, but it was typically always enough to cause disruption to our platform. Depicted here is a storm that evicted 280 nodes in the span of 11 minutes. The typical behavior of an eviction storm was not to evict a node once every couple of seconds throughout the duration of the storm. Instead, we would see a few large batches of between 50 and 100 evictions in an instant. When these storms started occurring, we were only running about 300 nodes in this cluster. So in other words, this storm evicted nearly every single node in this cluster in the span of 11 minutes. It was also common during these storms for nodes to be spun up and then immediately evicted again. And that would potentially trigger the back-to-back eviction issues that we talked about earlier. Here's an example from another eviction storm where our distributor deployment, which we usually run about 300 replicas, it goes all the way down to 25 replicas during a storm because replicas are evicted faster than they can be spun up. And clearly, if it normally takes us about 300 pods to handle the load, then 25 pods are not going to cut it. And we're going to see some sort of regression in the workload in the work that's being done by this deployment. So in conclusion, running all workloads on spot instances is not for the faint of heart. Spot instances really punish bad practices like not pinning versions and running single replica workloads. Spot instances will challenge our trust in the system. When an alert would trigger for us, we found it tempting to chalk it up to the fact that an eviction happened. But clearly, this is never a satisfying conclusion to an alert trigger when we run spot nodes. The eviction pattern that triggered that alert will happen again, and if we don't address the root cause, then the alert will just keep triggering. And by the same token, I think also spot instances increase the risk of engineer burnout. We did a tally back when we still ran exclusively on spot nodes, and we found that 70% of our reliability issues were either directly caused by or exacerbated by the fact that we run on spot nodes. Perhaps the only positive thing I can say, other than the money saved for spot instances, is that they have definitely made me a better engineer. I have become much more aware of how workloads behave when they're terminated. And now, when I create or review architectures and designs, I always think about what happens if I delete this pod and then delete it again immediately, or what happens if I just switch off this node, or what happens if we switch off nodes in 2 different zones at the same time. That's all I had to share.